Alright, very good morning everybody. So hope you are here to learn something new or brush up your knowledge. Let's see. So in today's video we will be discussing about series circuits, right? So mainly we have two kinds of circuits, two major categories like one is a series circuit and one is a parallel circuit. Okay, so in today's video we will be learning about series circuit. So let's see what is a series circuit. So for a series circuit, the components in your circuit will be cascade or connected end to end. So let's say you have a motor and that motor will be connected to another motor like this, right? So see, motor has two terminals in this case. So here is one terminal, here is the other terminal, and we wire in between the connectors, right? If it is a lamp, I could not cannot remember the symbol of the lamp properly, but let's say it is something like this. So it will be connected in this way, right? So the two terminals are linked, right, through a wire in between. So this forms a series circuit. Can you understand? So in between two terminals there will be a wire, right? So for most of the cases we can simplify our analysis uh, just to a resistor, right? So this is the load. Load means something that consumes energy, right? So you might have a battery. So battery is the source that supplies energy to this system. This resistor will be the load, so it consumes energy, right? So in a series circuit we have more than a single load most of the time, right? It can be even a single component, but to make it a basic kind of a circuit we will have two loads. So example, so we have one resistor like this and another resistor like this. So we have two resistors here, right? We also have the battery. So let's denote this one as R1 and this one as R2. So two resistors, right? And the ends are connected through a wire, right? So can you see? So the current, as you know, flows from the positive terminal, right? Like this, right? So that same current will enter this resistor and go through the resistive material, right? So the current will flow from left to right. Do you understand that? From left to right, right? Through this R1 and enter the next resistor from again left to right, right? Can you see? Current is the rate of flow of charges, right? So in this case, the charges will flow into the resistor and will come out of this terminal and enter the next resistor. So as we have two resistors, what can you say about the current? Current should be the same, right? Current is the same current flows, right? So let's build this circuit and see how it works. For an example, right, let's consider that R1 is equal to R2 and is equal to 1 kilo ohm maybe, right? You can take any value and let's see how much of a current will flow through this circuit, right? We are going to measure it. And now we also need a power supply. So power supply voltage, let's have it at 9 volts because it is very easy to find a 9 volts battery if you are doing this experiment at home, right? So we are going to build this circuit on the Tinkercad platform here. and see how it works, right? All right, so here we are in the Tinkercad platform. You can click on create circuit, that will take you to the main workspace, and in order for us to create this circuit, we have two resistors here, right? We have two resistors there, therefore we need to have two resistors dragged to our workspace like this. You can rotate the component by pressing the R key, or you can also use this one. So here I have one resistor. Let me copy that. So here you can add the value. Right now it is 1 kilo ohm, right? So let me add another resistor like this, Control C, Control V, right, and place it here. And you need to connect them by a wire. And also, as I said, we need a battery, right? Battery seems to be larger, so let's move this one over here, right? So let's go back to the circuit diagram and see. So now positive should be connected to one end of this resistor, and the negative should be connected to the other end of this resistor. So that's what we are going to build, right? So you can wire the positive. Let me take the red color for the positive and wire it here. All right, so let's also do another wire in black, which will be wired to the other terminal of this resistor. All right, so we simply created this circuit, and both these resistors have a value of 1 kilo ohm. So I hope that you know how to get the value of these resistors using the color code, right? So here the colors will be according to this one: brown, black, red, and gold, right? So those are the colors. So let's go back and do a little bit of study. So black, brown, red, gold, right? So you can go to Google and search color code resistors or something like that, and you will find some chart. You go to the images, I think, yeah, you can find some charts, right? I went to the Walmart accidentally. Okay, uh, we just need to get, see, so this is the color chart. So brown is having the value 1, so you put 1 here. Black is having a value of 0, red is having a value of 2, and for gold, the fourth band, right, usually gold or silver, it counts for a tolerance of how much I can't remember. For gold, was it 10? Gold is what? Gold tolerance, let's see, gold tolerance is 5%, right? Gold is plus or minus 5%, and silver is plus or minus fourth band. Yeah, gold tolerance, yeah, yep. Gold band tolerance, gold band tolerance, let's see. Let's see, what is it going to give us? 5%, right? Okay, so gold is going to give us a tolerance of 5%. All right, so that is correct. So let's see how we can get the value. So the color code will be 102, right? 102 means first two digits you write them as it is. 1, you write it here. 0, you write it here. And red, right, red will be the multiplier, so it is the power of 10, right? So you need to put the 10 here all the time, and for this index, you need to transfer this to here, right? So it will be 10 times 10 to the power 2, and it will be in ohms. So what is it? 10 times 100, right? Gives us 1000 ohms. So we have a 1 kilo ohm resistor. So in kilo ohms, 1000 ohms is 1k, right? So that's what we have here, right? All right. So when we start the simulation, let's see what happens. Something is happening, but we cannot see the result, right? So in order for us to see the results, basically we are going to measure the current or the rate of flow of the charges, right? So to measure the current, you need a multimeter. So that's why I have a multimeter here. If you need to measure current, the multimeter should always be placed in series. What does that mean? So let's see how we can place the multimeter, right? So you have two resistors, this is 1k, and we have another resistor which is 1k. We need to measure the current, so the ammeter should be placed in series. It can be placed anywhere in the circuit, right? And you have the battery, which is the 9-volt battery, right? All right, so this is the circuit diagram, and we are going to measure the current. So do you know how to calculate the current of this circuit? So basically what you need to do is you need to apply Kirchhoff Ohm's law, right? V equal IR, right? Simply we can use this one, right? So when there are two resistors cascaded end to end like this, it can be combined, right? So if you have a resistor plus another resistor, the overall impact of this connection will be the combined resistance R1 R2. So R total will be R1 plus R2. Is that clear? Right. So if that is the case, we can simplify this circuit by replacing these two resistors with a single resistor of 2k. Alright, so we have a 2k resistor connected to a 9-volt supply. So if we apply V equal IR, now this looks like a single component. For that component, we apply this equation, right? So when we apply that equation, what happens is we can find the current. So for us to find the current, we can apply Ohm's law, right? So in that case, what we do is we equal IR for this combined resistor. So voltage applied will be 9 volts is equal to I times RT. What is RT? RT we found it as 2K. So when doing your calculations, it is always a good practice to make sure that we substitute all the required parameters in the base unit. Is this a base unit? 2 kilo ohms? No, right? No. So therefore RT should be in base units, which is 2000 ohms, right? 1 kilo ohm is equal to 1000 ohms. Therefore 2 kilo ohms is equal to 2000 ohms. So that's why we have to put 2000, right? 9 equal I times 2000 ohms. So 9 divided by 2000 will be I. What is it? 0. What divided by 2? This will be 4.5, and at the bottom it will be 1000, right? It will be 1000, right? 4.5 over 1000 will be your answer. 0.045 or something. 4.5 divided by 1000, 1, 2, 3. I think, yeah, 4.5 milliamperes. Let's see. Yeah, that's what's going to happen. So it will be 4.5 milliamperes, right? So I will be, just to make sure, 1000 and multiple 1000 just of 4 point yep 0 0.00450 amperes. So this is in amperes, right? So it is convenient for us to write it in milliamperes. So we multiply by 1000 to convert amperes into milliamperes. So 4.5 milliamperes, or else you can also write it as I equal 4.5 into 10 to the power minus 3 amperes. Everything is the same, right? So the current should be 4.5 milliamperes based on this one. So now what we are going to do is we are going to measure it. So see the connection, right? Positive, right? Going to supply the current to the circuit, so charges are going to go through the meter. It is like a flow meter. It measures the flow, right? So how many amperes are going through this point. So we have to add the ammeter in series, right? Always in series. So charges flowing out of this positive terminal enters this ammeter and leaves the ammeter, right? During the process it measures the amount of charges that will be flowing through that device. So that's why we have to break open the circuit somewhere just to measure the current, right? So we will break open the circuit at a point somewhere here, right? All right, so let's break open the circuit somewhere here. So we have to maintain the same thing, but right now we have to add this device in the middle. So we have to change this to amperage, right, to make sure that it is an ammeter which is capable of measuring current. So current leaving the battery is supplied to the ammeter like this, and that same current will leave this device, like it will go through this device, right? It will go through this device. And if I run the simulation now, as we did the calculation, you can see the value as 4.50. Can you see? So this is the exact same thing that we got out of this calculation as well, right? All right, so I hope that is clear to you, so how it works. All right, so let's take another example, right? So okay, let's take the same example and see what happens with the voltage, right? So we had, our original circuit was to connect two 1k resistors into an cascaded like this, 1k 1k. So we connected it to a 9 volts battery, 9 volts battery, right? So what happens to the voltage? So in a series circuit, right, in a series circuit, current is the same, right? Current is the same, we saw that, right? And voltage will divide, okay, voltage will divide. So I said that the current is the same. What does that mean? It means that when we have the ammeter, so we can again put both the resistors here, right? Set R1 and R2, R1 and R2, right? current is the same means like no matter where we place the ammeter, it will show the same reading. So if we put the ammeter in between these two components like this, if we break open the circuit at any point and insert an ammeter here or here, it doesn't matter, right? It should show the same value. So even if you had an ammeter here, it's the same flow, right? It's the same flow that is going to be there throughout this whole circuit. It's like an entirely connected pipeline, right? So due to that, the current will be the same. So we can do this as an experiment. So here we have one ammeter. Okay, let's stop the simulation and see. We need to space things a bit, and let's copy this ammeter, paste it here, paste another ammeter here, right? So we have like 1, 2 and 3 ammeters now, right? All right, so let's see what we can do. So we can disconnect this wire, right? The current now comes out of this positive terminal, goes through this ammeter, enters this resistor through this terminal 1 and leaves this terminal 2. So that current leaving that resistor should always enter from the positive side of this device. So to make it clear, you can mirror this component, otherwise you cannot mirror. Yeah, it's not a that option is not available, so therefore you need to wire it to the positive. So remember that to see a positive value in this display, the usual convention is that current should enter through the positive terminal of the ammeter, right? And also the current leaving the ammeter should uh, be through the negative lead or the black lead, right? So you can this is also red, right? It's the same current. All right, so let's run this simulation. So as you can see, right, both the readings are the same. So irrespective of the point where we insert the ammeter, the current remains the same. Can you see? It's the same current. Even if we add this ammeter somewhere here, it should still show us the same value. So that's why we say that the current is the same throughout the circuit, right? So the current leaves this node, right? So it leaves that node and it should enter the positive terminal. So that's why we will make this connection, and to leave this ammeter through the black lead. And just to make it clear, let's put this one as black. Okay, and now you should see the same value on all the 3 ammeters. Can you see? When the devices are cascaded end to end, right, the same current flows. So can you see that this device is also acting like another component? It also has 2 terminals, and this resistor is also having 2 terminals, so and their ends are cascaded. So that's why we have the same current throughout the whole circuit. But as I explained to you, right, here you can see that the current in this situation will be the same, but the voltage will divide. As I explained to you, the voltage will divide. What does that mean? So if both the components are having the same resistance, right, if they are having the same resistance, what will happen? The voltage will be divided. So battery has a voltage of 9 volts, so it will be divided among the 2 resistors, right, among the 2 resistors. So what will happen if they are going to have the same value? This will have 4.5 volts and this will have 4.5 volts. It's the same voltage divided by 2, right? So irrespective of the value, if both the values are the same, the voltage divides based on the proportion of the resistors, right? Based on the proportion, right? So, and also voltage across a component is directly proportional to the resistance, right? V equal IR. So even if you had, let's say, 3.3k here, 3.3k, the voltage will be 4.5 and 4.5, right? It doesn't matter, right? Because they are having equal values. But if the ratios change, then something different will happen. So first let's try to measure the voltage. So unlike the ammeters, voltmeter should be connected in parallel. Remember that this is very important, right? So if we need to measure the voltage, you should probe this device by using a voltmeter like this, right? Voltmeter is always connected in parallel to the component, okay? Something like this. You cannot put a voltmeter in series, right? That is wrong. So instead of doing this one, if you put a voltmeter somewhere here, makes no sense, right? So you should always add the voltmeter in parallel to the respective component like this. So let's do this experiment, right? Let's do this experiment and see whether we are getting 4.5 volts across each resistor. So for us to do that, we can remove these ammeters because we no longer need them, and here you can connect them into n. Let's have red here and connect the positive to this end, and we will connect the negative as well, something like this, right? That's okay, that is going well. And we will move the battery, and let's add the voltmeter. So bring in a multimeter, change the mode to voltage. It is all by default it is set to volts, so that is not a problem. So we add 2. As I said, which side is the positive side? Here I did a mistake, right? So this wire needs to be red color just to avoid any confusion, right? So positive should be connected to the higher polarity side. So here, as you know, positive, it is more close towards the positive terminal of the battery, so this side will be positive and this will be negative. So let's wire this one somewhere here, and you can change the color to green maybe, just to make it clear, right? Okay. And let's measure the voltage of this resistor and see what's the value. 4.5, right? Right now we are not measuring the voltage of this resistor, so anyway it's half of 9 volts, so definitely the other half should be across this resistor. So let's see that value as well. So again, which side is more positive? As you can see that this wire is ground, which is negative, so we need to connect the negative lead here or here. It's the same, so let's connect it here, and we will wire a right wire to the left side of this resistor. Just to make it clear, I will move the wire from this side, okay? Just to make it clear. Alright, so let's start the simulation. So you can see that now both the voltmeters are giving us 4.5 volts across them, as expected, right? As expected. because they are having the same value. So anyway, let's try to change the value, right? So let's try to make this one as 100 kilo ohms, and what else, we will make this one as 100 kilo ohms, and you will see that when you do that, both the voltmeter still shows the same value. Current will change because the resistance of the overall circuit is now different, right? So but the voltage will be divided in the same proportions because both are having the same value, right? So we found that the voltage will be 4.5 volts across each resistor, right? So that is what is going to happen. If we add another resistor, suppose that you had another 100 ohms resistor, what will happen? 9 volts, right? Now if we had another resistor, let's say somewhere here we had another resistor here which is also 100k, 100k and 100k, and voltage across this resistor will be what? This is now not 4.5, it will be 3 volts, 3 volts and 3 volts divided equally among the three resistors. 3 volts, 3 volts plus 3 volts is equal to 9 volts in total, right? So that is what is going to happen if we had another resistor. I can even add that resistor and show you. Control C, Control V. I don't need to measure it, it will make this messy. These resistors, they don't have any polarity, so you don't have to worry about that. Let's change this one to red and this one to black, just to make some sense out of the colors, right? So if I start the simulation now, you see 3 volts across this resistor, 3 volts across this resistor, and if you still measure the voltage across this resistor, it will be 3 volts, right? That should be clear for you. Yeah, I think that is clear, right? So that is how the voltage will divide. But just to explain the final part, just to make this complete, I don't want to put this one to a level that is not understood by anybody. So let's see how we can calculate the voltage of an individual resistor, right? So first what we need to do is we need to determine the current of this entire circuit. So what will be that current? So to calculate the current, as there are three resistors, R1 plus R2 plus R3, all in series, what is the total resistance? 100 plus 100 plus 100, 300k. 300k means 300,000 ohms, right? This is the total resistance. Alright, so now we can simplify this. This will be looking like R1 plus R2 plus R3, and we are still applying 9 volts like this. That 9 volts will be applied across this equivalent resistor, which is around 300,000 ohms, right? So if we apply Ohm's law for that resistor, we equal here. What is the voltage applied across that resistor? It will be 9 volts. 9 volts applied across I times 300,000 ohms, and I will be 9 over 300,000, right? So you can divide by 3. B, if you divide 9 by 3, 3, and if you divide this value by 3, it will be 100,000, right? So 3 divided by 100,000, right? How many zeros? It should be 4 zeros, I believe. 0.000. 0.03 amperes, right? Is it correct? I just want to check that, right? 9 divided by 300,000, 1, 2, 3. Alright, 0.4 zeros, no? Yeah, 4 zeros, right? If it is in milliamperes, so it should be microamperes 10 to the power 6, right? It is like 30 microamperes, or it's also equal to multiply by 10 to the power 3. Yeah, so it is around 30 microamperes, right? Or else you can also write the same thing as 3 into 10 to the power what? How many 10 to the power 10 to the power 5, right? Amperes minus 5. So you can calculate the current like that, right? So it's a very small current. So once you know the current, right? Once you know the current, you can find the voltage across each resistor, because you know that the same current flows through each resistor, which is 3 into 10 to the power minus 5 amperes flowing through each resistor, right? So now the same current, right? Same current. So if you measure the current using an ammeter, by placing an ammeter somewhere here, you will see this value. Now in order for you to get the voltage across a resistor, if you don't know the value experimentally, you can apply that current flowing through the circuit will be the same current flowing through this resistor, so you can apply V equal IR. So we assume that we don't know V, right? Because we don't know, let's say we don't know how it divides for now. So in that case, V is unknown, I is 3 into 10 to the power minus 5 times R is 100k, so 100,000 ohms, right? So here 10 to the power minus 5 and this one will cancel out, so V is 3 volts. Can you see how it comes? So if you repeat the same calculation, you will get 3 volts here, so let's 3 volts here, right? So that is how you find the voltage. I mean, I can go on and on, but just to make it clear and simple enough, this is how series circuits work. I hope that you learned something out of this video. So thanks for sticking around and hope to see you soon.